Hi, welcome to Intermolecular Forces, Solids and Liquids. My name is Dr. English. Today we're going to talk about bonding in solids. Specifically, we're going to talk about structure of solids, covalent network solids, ionic solids, molecular solids, and finally, metallic solids. Variations in bond type lead to different structures in solids. Two different types of solid structure and their properties are considered here. The first one that we're going to talk about is a crystalline solid, and the definition of a crystalline solid is a well-defined arrangement of atoms, ions, or molecules involved in the structure. The next type of solid that we're going to talk about is an amorphous solid, and an amorphous solid is defined as particles in the structure that have no order, do not stack well together. One example of an amorphous solid is this rubber duck right here, and the other one is this glass. Now let's talk about different classifications of solids. What you need to know are the types of forces involved in the structure and the general characteristics associated with the solids. Specifically, we're going to talk about covalent network solids, ionic solids, molecular solids, and metallic solids. Let's start out by talking about covalent network solids. Structures composed of group 14 atoms, such as carbon and silicon, covalently bonded together in a continuous network. That's our definition. This type of structure is based upon the tetrahedral unit, where all of the atoms are bonded together with very strong covalent bonds in a large macromolecule structure. As a result, such structures are typically very strong and hard, and we see that in a diamond and also silicon binding to itself. Graphite has a layered structure, where each carbon atom is bonded to three others in each plane. The structure leads to specific properties. The first is that it will conduct electricity only in one plane. In the graphite structure, each carbon is only bonded to three others. This leaves one of the outer electrons free. Each carbon atom has one such free electron, and these are spread out over each layer. In other words, they're known as being delocalized. This leads to a sea of electrons similar to that in the metallic structure and graphite's ability to conduct electricity along the layers. Since the electrons cannot move between layers, there is no conduction in the vertical plane. Graphite can also be used as a lubricant. Weak dispersion forces hold the layers in graphite together. These are represented by the dotted lines on the diagram. As a result, they can slide over one another, making graphite a good lubricant. Now let's talk about ionic solids. In the ionic structure, the lattice of ions is held together by strong electrostatic interactions between positive and negative ions. As a result, strong bonds give ionic solids high melting points. Ionic solids are only able to conduct electricity when in the molten state or in solution, aqueous solution, meaning something's been dissolved in water. Since in the solid, the ions are rigidly held and cannot move. This is a very important point, and you need to pay a close attention to these phase symbols by the compounds. So up here we see this is representing NaCl solid, where it's all closely packed together, held together by electrostatic forces. That's representing a solid. But NaCl liquid means that sodium chloride has been melted into a liquid and electrons are able to move. Compare that to NaCl aqueous, which means the solid sodium chloride has been dissolved in water, and therefore the ions are able to move. Solubility of ionic compounds and hydrates. The positive and negative ions found in an ionic solid explain how and why ionic solids have the ability to dissolve in water. When an ionic solid dissolves, the polar water molecules penetrate the lattice and attach themselves to the ions. This process is known as hydration, and we see this represented symbolically in this image below, where you have a positive sodium ion surrounded by water molecules. Notice that the oxygen end of the water molecule, which is slightly negative, is facing inwards towards the sodium ion. The opposite would be occurring if we had a chloride ion in the center. If there was a negatively charged chloride ion in the center, The hydrogen end of the water molecule would be facing inwards. Molecular structures. In a structure of iodine, only weak London dispersion forces keep the iodine molecules in place. Solid iodine has a very low melting point, since only weak interactions occur between its molecules. Iodine is also a non-conductor, since no charged particles are present. In solid water, the strongest intermolecular force present is hydrogen bonding. Ice has a much higher melting point than other molecular solids, since these strong interactions occur between its molecules. Water as a pure substance does not conduct electricity to any measurable degree. Metallic solids. Metallic solids are held together by metallic bonds. The simplest description of metallic bonding is the interaction of positive metal ions, which we see right here, with surrounding sea of electrons, which are represented right here. This sea of electrons is a result of delocalized electrons. A delocalized electron is typically a valence electron associated with a given metal. As metals typically have low ionization energies, these valence electrons have the ability to move throughout the metallic crystal. Metals tend to be good conductors of electricity and heat. The metallic crystal structure of a metal also allows for flexibility of these bonds and makes metals malleable and ductile. And here we have, summing all of this up, a little overview of the difference between crystalline solids and atomic solids, breaking them down into molecular solids, ionic solids, your nonpolar compounds, your metallic compounds, and your network covalent compounds. So what did you learn? We went over the structure of solids, we talked about covalent network solids, ionic solids, molecular solids, and metallic solids. Need more help? Feel free to contact me. Have a great day.